We next generalize the notion of the radical of an ideal like this. Let A be a ring and E be a subset of A, any subset. Now previously we had an ideal, now we have any subset of A. Then we define the radical of this subset E in exactly the same manner as before. That is, R of E is the set of those ring elements X such that X to the power n belongs to E for some positive integer n. But unlike the previous case where the radical of an ideal turned out to itself be an ideal, R of E in general is not an ideal of the ring A. We still have this fact though. If this E alpha is a family of subsets of A where you understand that this alpha varies over some index set which we are not writing explicitly, then the radical of the union of the elements in this family is equal to the union of the radicals of the individual elements. Let us prove this. The proof is very straightforward. Let us start by taking any element x here in the radical of the union. Then by the definition of radical, some power of x where the exponent n is a positive integer belongs to this union. And when something belongs to a union, it belongs to at least one of the sets. So that way, x to the power n belongs to E alpha for some index alpha. But then again by the definition of radical, x will belong to the radical of E alpha, and that is why x belongs to the union of all such radicals. If you want, you can use something else here. I think it would be better if you write beta here. That is because the nature of alpha is that of a variable here, but this way also you can write if there is no scope for confusion. If it is not confusing you, then it's okay. So we see that any element x here is also here, and that is why this is a subset of this. Now we go for the reverse inclusion. Conversely, let us take any element y in the union of these radicals. So then y will belong to one of the radicals. Y belongs to R of E alpha for some index alpha. Now since y is in this radical, some power of y will belong to this set E alpha for some positive integer index n. But then if it belongs to E alpha, it also belongs to the union of all the E alphas. And that is why again by the definition of radical, y then belongs to the radical of this union. And that is why any element here is also here. So this is the subset of this. Now combining the two containments, you have equality. Next we have this proposition, proposition 115. Consider a ring A and in it let D be the set of all zero-divisors. Then D equals this union. D is the union of the radicals of the annihilators of X, where X is any non-zero element in A. So here you need to go back to the definition of annihilator. Do you remember that in general we define the annihilator of an ideal? Here we however see a single element. So this means the annihilator of the principal ideal generated by X. So let's now see the proof. The proof starts with this observation. Clearly D is contained in the radical of D. This property which we saw is true for radicals of ideals continues to be true for radicals of general subsets of a ring as well. So you already know how that one is true. So here also the argument is same. So we are not going to go into that. Okay, you see it yourself. Now next what we do, our aim is to prove now that the reverse inclusion is also true. So as such we take an element, any element x in the radical of D. Then by the definition of radical, some power of x will belong to D for some positive integer n. If you want, you can write here n greater than 0. N being greater than 0 and being greater than or equal to 1 are the same because n is an integer. Now we can assume without loss of generality that n is the smallest such positive integer for which this will happen. And the reason for the existence of a smallest n is your well ordering principle. Now, even when n is smallest, n can be 1. Okay, that is one case. Now, if n is equal to 1, then x to the power n is just x. So, we are directly getting the fact that x belongs to D, which is what we want. We want to show that this arbitrary element of R of D is also in D. But what happens if n is not equal to 1? So, next we consider that case. Let n be greater than 1. Now, what does it mean for x to the power n to be in D? D is the set of all zero divisors. So, x to the power n is also a zero divisor, and that's why there will exist a non-zero element y in A, such that if you multiply that with x to the power n, you are going to get 0. Now, note that you can write this product like this also. X times x to the power n minus 1 is x to the power n. Note one more thing, that n is a positive integer greater than 1. So, the least n can be is 2. So, even when n is 2, n minus 1 is 1. So, that is why this split is okay. Alright. Now, this quantity, this element, this product inside brackets may or may not be 0. What happens if it is equal to 0? If this is equal to 0, then owing to the fact that y is a non-zero element in the ring, we get this, that x to the power n minus 1 is also a zero divisor. So, it belongs to D, but that creates the problem, because n minus 1 due to this inequality is also a positive integer just like n, but it is smaller than n, and even then x to the power n minus 1 belongs to D. So, the minimal nature of n is violated here if this happens. So, that means it cannot happen, so it has to be a non-zero element. So, now what are we getting? X times a non-zero ring element is equal to 0. So, that means x is a zero divisor, and that is why x belongs to D in this case also, just like the previous case. So, in general, any element x here in the radical of D is also in D. So, that way R of D is also a subset of D. So, combining these two containments, you get equality. And now we are going to recall something about the set D itself, which we saw before. So, now we continue our calculation from here. D equals R of D, and D itself equals this union. So, this is what we are recalling from before. We already know that the set of zero divisors equals the union of all the annihilators of non-zero elements in the ring. And by what we proved in the beginning of this video, you can take R inside, because this is the radical of this union. So, that will be equal to the union of the radicals of these annihilators. That's how you get your desired identity. So, let's just end this video here itself. There are a few other things that we will see next week. So, see you next week with those things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.